Good morning to one and all. I welcome you all to the Thermodynamic course. Myself, Arun Kumar, Assistant Professor, Aeronautical Department from MLR Institute of Technology, Hyderabad. So, in the previous lecture, we discussed about the derivation of mass balance and energy balance equation. In today's lecture, we are going to discuss about one numerical problem in terms of application oriented numerical problem on steady flow process. So if it comes under steady flow process, obviously we are supposed to apply the steady flow energy equations as well as steady flow mass balance equation. See, this is what the given problem. Let me read the problem. See, in a gas turbine, right? Gas enters the turbine at the rate of 5 kg per second and with velocity 50 meter per second, and the enthalpy also they have given, right? So these are all entering the turbine. See, first one enters the turbine. See, before the turbine actually we supposed to have a kind of heating process, heat energy process, say for example boiler or compressor chamber we supposed to consider, right? So with that the enthalpy actually how much actually we got 900 kilojoule per kilogram, right? And leaves the turbine, right? So these are all the entering conditions they have given. So entering conditions they said velocity they have given, mass flow rate they have given, and enthalpy also they have given. And leaves the turbine with 150 meter per second, right? So the turbine, the expansion process takes place. So because of that expansion, what will happen actually? The gases get expanded so that it accelerate the flow, and because of that what is happening actually the velocity get increases. That is what 150 meter per second, and we have converted this available energy or enthalpy, internal energy, right? We have converted that into a form of kinetic energy so that the enthalpy get decreases. So that is what the law of conservation of energy. So how much enthalpy which is entering? 900 kilojoule per kilogram with 50 meter per second, right? It is converted into 150 meter per second, so that where we are getting that energy actually, we are not supplying any heat energy to the turbine. Got it? So that is the energy conversion takes place. So from that 900 kilojoule, some energy is consumed, that is converted into kinetic energy. So obviously the enthalpy get decreases while leaving the system, right? The loss of heat from the gas to the surroundings. See, the turbine is not well insulated, right? So because of that, some heat transfer takes place from the system to the surrounding, right? So from the system to the surrounding also some heat transfer takes place. So because of that, some loss is taking place. That loss actually what they are telling with respect to the surrounding, it is nothing but 25 kilojoule per kilogram, right? And they have given that hot gas or gas, whatever it may be, they have given those gas values constants also, right? So this is what R equal to 0.285 kilojoule per kilogram Kelvin, universal gas constant, and Cp value they have given. See, if I know Cp and R, actually I can able to calculate the Cv also, right? And the inlet conditions to be at 100 kilopascal and 27 degrees Celsius, right? See, the inlet conditions also they have given with respect to 100 kilopascal and 27 degrees Celsius. So the inlet is nothing but actually we can consider Ti. This is what inlet T, so which is 27 degrees Celsius Ti, and this is actually Pi, right? Or P1 also, no problem. With respect to one also you can able to say Pi or P1, right? So the inlet conditions they have given. Determine the work done and the diameter of the inlet pipe. Got it? So determine the work done. So what are the parameters we supposed to calculate? Work done and diameter of the inlet pipe. So what is that work done actually? Mechanical work done always, W. And diameter of the inlet pipe. So inlet pipe in the sense we are having, they have given the pipe, right? So pipe in the sense we are having with respect to the circular cross section. So obviously the diameter also we supposed to calculate, right? So with respect to that, the diameter of the inlet only in the sense Di I can able to say. See, from this two parameters, which one to find parameters, work done and diameter of the inlet pipe. See, for the work done, we supposed to apply the steady flow energy balance equation, right? For the diameter of the inlet pipe. So diameter in the sense actually it deals with the area. So obviously I supposed to consider only with respect to which one? I supposed to consider mass balance equation. The mass balance also the simplified one or the other form of mass balance equation I supposed to consider after applying the continuity equation. That is what we have derived. What is that actually? M dot 1 equal to M dot 2, or we can say rho A V R C, right? Rho A, we can able to say rho A C equal to rho A C. So what is that? Rho 1 A1 C1 equal to rho 2 A2 C2, right? So with respect to that, I can able to find out the area, right? Why? Because mass flow rate they have given. So any one conditions, so both will be constant. What is that? M dot. Both will be constant. So any equations I can able to get. So rho 1 A1 and C1 also I can able to get. So with respect to that, I can able to find out the area. So this is what actually the overview of the problem. See, we are having with respect to that, right? We are having the turbines actually. That turbine they have given the inlet pipe and as well as they have given the outlet pipe, right? See, listen here. The thing is that the potential energy they didn't mention in the problem. So which means it is negligible. No need to consider the potential energy, right? See, the heat losses from the system to the surrounding, which means it is not insulated. In that way, we supposed to consider. So the heat is transferring from the system to the surrounding. So it is obviously in terms of negative we supposed to consider. That is our sign conversion. So what is that? Q actually they have given Q equal to minus 25 kilojoule per kilogram. So in that schematic diagram, actually, if you mention all the given data, right? So with respect to what is this C1, C2, H1, H2, right? And they have given here P1 and P1. See, I have mentioned here I. Okay, no problem. I or 1, whatever it may be, right? And we are having D1 over here, and this is D2 we are having, and we are extracting the mechanical work done. That is what the turbine purpose, right? To extract the mechanical work done. Okay, so obviously it must be in terms of the positive we'll get, right? So in this way we need to apply the energy balance equations, so that I can able to get the which one? I can able to get the work done, the mechanical work done. See, while deriving that steady flow energy equation, I have considered the Q equal to nothing but we have applied energy to the heat energy to the system. But here the heat is loss. That is why I have considered Q equal to negative. And in the consideration we have considered the mechanical work output we are extracting. Here also with respect to the turbine we are extracting the mechanical work output. So that is why I have said in terms of positive. Got it? So this is not the simplified form of given problem, right? So after that we know the steady flow energy equation. By applying the steady flow energy equation, right? So we can easily able to solve the problem. So this is what the given data which we discussed right now. So here actually it's supposed to be M dot, not M. Okay, M dot is nothing but flow rate, mass flow rate, right? And they have given C1, H1, C2, H2, R, CP, whatever the Q. See, Q is nothing but actually they have given in terms of negative. We need to consider as negative, right? So that is what they given in the problem. Got it? And why they have given P1 and T1, that we will see, right? For the continuity equation, you need to calculate the rho 1. So that is why they have given this P1 and T1, right? See, what are the parameters we need to find out? First, mechanical work done and diameter of the pipe, D1 we will consider, right? D1, right? Solution is nothing but by applying the steady flow energy equations. What is the steady flow energy equations we are having? So this is your standard steady flow energy equation. H1 plus C1 square by 2 plus Z1 into Z plus Q is equal to this with respect to the leaving the system, right? So after that actually I supposed to consider what are the data we are having, right? So what are the data I'm having? We are having H1 we are having, C1 square, C1 we are having, Z1 there is no Z1. So this two Z1 and Z2 negligible. The difference is negligible, right? See, listen here. Here actually they have mentioned in terms of 900. Actually, what is that they have given in terms of kilojoule per kilogram? Kilojoule per kilogram. But while evaluating with respect to which one, kinetic energy, while evaluating with respect to the kinetic energy, we'll get joule or joule per kilogram. See here the masses actually we have taken with respect to the prescribed format. See, we can able to take the steady flow energy equation in terms of three format. One is nothing but with respect to standard one. What is that? Kilojoule or joule. Another one is nothing but kilowatt or watt. Another one is nothing but we are having kilojoule per kilogram or joule per kilogram. Right? Got it? So in that way we have taken. See, but the enthalpy they have given in terms of kilo, but the kinetic energy which we evaluated is nothing but always joule per kilogram only in the standard format. Right? So kinetic energy is nothing but joule. We can't able to get in terms of kilojoule or something. Why? Because there actually we can't able to implement Cp value or Cv value over there. Only the thing is that half mv square we are having, the general equation we are having, right? So with respect to that half mv square actually, right? So we can able to get only with respect to in terms of which one, joule, right? Kg meter square per science square is nothing but actually we are having only in terms of joule. There we are not having any kilo values over there. That is why, see, we have in order to convert joule per kilogram, right, into kilojoule per kilogram, just multiply with respect to 10 power 3 and divide by 10 power 3, right? So if it is multiplied with the 10 power 3, now I have the kilo over here. So that is why that 10 power 3 I have taken outside. Why? Because H is given in terms of kilojoule per kilogram. 25 also. What is that? Q is given as minus 25 kilojoule per kilogram. See the problem, right? So there also they have given kilo. So that is why this kinetic energy parameter also we supposed to convert in terms of kilojoule per kilogram. Already it is C1 square by 2 is nothing but in terms of joule per kilogram we are having. Now to convert that kilo, multiply and divide by 10 power 3, right? So there actually I am having kilo over here. I can take common parameters right now. So I can able to sum up all these things, right? Now I am having kilojoule per kilogram. Here also I am having kilojoule per kilogram. If it is enthalpy is in kilojoule per kilogram, if it is in terms of joule per kilogram, we can't able to sum up, right? So that is why that conversion we have used. That is why we have 2 into 1000. That is why 2000 they have given. Got it? Right? So with respect to this, I can able to get which is unknown, W is unknown. So if I solve the problem, I'll get W equal to in terms of 465 kilojoule per kilogram. Right? So this is what in this way we supposed to solve the problem. So this conversion, be careful. Why? Because that is with respect to kinetic energy always is nothing but a joule or joule per kilogram only. We need to convert other parameters actually I have given in terms of kilojoule per kilogram. Otherwise you do in vice versa manner also, no problem at all. You can convert this kilo is nothing but mere value. You can multiply 900 into 10 power 3. But the thing is that we will get in terms of 6 digit or 7 digits values. Right? So that is why not to avoid that confusions, we have converted that into kilojoule per kilogram also. Right? So in this way we have evaluated the work output, or we can say mechanical work done. Right? So with respect to that diameter also, we can able to calculate with respect to that which one, m dot equal to rho 1 a1 c1. Right? So with that we can able to calculate the d1 also. So thank you one and all about today's lecture. Right? So we'll see in the next video. Thank you.